Prakash for inviting me. So, okay, this talk is on Chern-Simons theory with vector fermion matter, and okay, essentially we'll just study UN Chern-Simons theory coupled to fundamental fermions in large N limit, and the work is based on this reference archive written in collaboration with Simone Giombi, Shiraz Minwala, Sandeep Trivedi, Spencer Wadia, and G.E. So what will the technical calculations will be? We calculate the free energy of the theory at finite temperature for all values of the 't Hooft couplings. So the theory turns out to be exactly solvable, and we'll briefly study the operator spectrum of the theory and argue that its holographic dual, should it exist, would be a higher spin gauge theory. But before I do that, I'll just go over some very elementary sort of context just to set up why we're sort of studying it. So, okay, QCD and the large N limit. So we study. I mean, I'll just skip. So to study, yeah, I'll just skip all of this. So the starting point for the talk is a simple observation that lines of fixed points are plentiful in 3 dimensions, and this is not true in higher dimensions, such as ADS4. And let's see the construction. So the classic example is ABGM theory, which is based on the Chern-Simons kinetic term. So the question is, why is ABJM conformal? And it's just a simple argument. Okay, K is an integer because it's a Chern-Simons coupling, and supersymmetry relates all other couplings to K, so they can't run. And that's a much simpler argument than you would say use for super Yang-Mills or something like this. So let's consider an even simpler class of non-supersymmetric Chern-Simons theories with matter. Say you just study a level K UN Chern-Simons theory coupled to a single fermion in any representation of the gauge group. The only gauge invariant operators you could put in the Lagrangian are just the kinetic term for the fermion and the mass term. So it just depends on 2 discrete parameters, K and N, and the physical mass M. If your energy is much higher than the mass, you have a conformal field theory parameterized by 2 discrete parameters, K and N. And just as in ABGM, they coalesce into a fixed point, a fixed line in the 't Hooft limit lambda equals N over K. So in 4 dimensions, I mean, if you want to have a line of fixed points parameterized by or any other higher dimensions, if you want to have a line of conformal fixed points that's not supersymmetric, I mean, I don't know how do you do it aside from having a parametrically large number of flavors or something like this. But in 3 dimensions, as you see, it's very easy to have lines of conformal large N field theories, and obviously this is sort of intriguingly related to non-supersymmetric quantum theories of gravity in ADS4, perhaps. And then let me just emphasize that a variety of such non-supersymmetric fixed lines exist. Choosing fermions that transform in the adjoint representation of UN gives one such fixed lines of theories. Choosing fermions that transform in the bifundamental yields another example. And if you choose the Chern-Simons levels to be equal and opposite as in ABGM, you get sort of a minimal non-supersymmetric example of conformal of analog of ABGM. So again, in super Yang-Mills, you can't just, I guess, throw away the scalars and keep conformal invariance. But in ABGM, you can throw away the scalars and throw away the whatever the SO8 symmetry, so you just have a single fermion in the bifundamental representation and of UN cross UN, and okay, that it would be interesting to, and that's something new about ABGM, and it's as opposed to super Yang-Mills and 3 dimensions.
Shiroman, the way you put it looks like with fermions you can do almost anything and it will be conformal. Can you put any fermion representation?
As far as, I mean, this is the argument, right? You just what can run? I mean.
Okay, but and if you put scalars, it's different, right?
If you put scalars, okay, then you have the phi to the 6 coupling, and the phi to the 6 coupling in principle can run. But I think Arani has looked at the theory of scalars, and you can still have your critical values of the phi to the 6 coupling for a given value of the 't coupling. But for fermions, it's just trivial. For scalars, you might get conformal theories if you do some work. And of course, if once you have just even a little bit of supersymmetry, if the Yukawa couplings and the scalar terms are related to K, then they can't run. So the point is, conformal field theories in 3 dimensions are really easy to construct, and they're plentiful, with and without supersymmetry. So okay, it obviously it's an interesting program that many people are studying, and particularly with supersymmetry. But what we here we'll sort of consider sort of the simplest non-supersymmetric theory you could try studying, which is just UN level K Chern-Simons theory coupled to a single fundamental fermion. And that's okay. The Chern-Simons gauge field has n squared components, so you expect. So it looks like a matrix model superficially, but Chern-Simons theories gauge fields don't propagate, so the only actual degrees of freedom are the vectors of the fundamental fermion. So the theory is actually a vector model and not a matrix model, and large n limits of vector models are easier to solve than their matrix counterparts. And in this case, the theory is more or less sort of exactly solvable. Though of course, the price you pay for going to vectors at the dynamics is less interesting, but nevertheless, this is the starting point. So the simplicity of the vector model in the large n limit combined with the crucial choice of light cone gauge allows us to derive several exact results. So we'll, although typically people are interested in the free energy on S3, what we're able to calculate is the free energy on R2 cross S1, which is just the theory at finite temperature physically. And we can calculate that exactly as a function of the 't coupling. And we'll also talk about its holographic dual a little bit and argue that, okay, unlike in the case of super Yang-Mills, where in the free limit, okay, it has infinite number of conserved currents, so you expect it to be dual to a higher spin theory, but as you increase lambda, those currents disappear and you get an Einstein theory. Here we find that the dual sort of has to be higher spin even as you turn on the coupling, which is interesting or not interesting depending on your point of view. Okay, so let's go over the free energy calculation. So we're working in Euclidean space. The action for the theory.
Sorry, just to go back 1 second.
Yeah.
You said the dual will be higher spin if you do what?
So
Just the last comment.
So what I'm saying is, you might ask, what is the holographic dual to the theory? So first, going back to super Yang-Mills. Okay, at large lambda, the holographic dual is supergravity, type 2b supergravity on ADS 5 cross 5. At lambda equals 0, it's type 2b string theory on ADS 5 cross S5, and you might want to write that as some sort of a higher spin gauge theory with matter, because there's an infinite number of conserved currents in the field theory. And the idea is those higher spin gauge theories somehow get massive or as you increase lambda. Okay, so here what we'll do is the free theory in this case is known to be dual to a particular higher spin gauge theory, and we will ask what happens as we turn on lambda. And the idea is, in this case, those higher spin gauge theories sort of have to persist. So if a holographic dual description exists, it would have to be a higher spin gauge theory and not an Einsteinian theory for all values of lambda. So then the intuition is that, okay, vector models are dual to higher spin gauge theories, and matrix models might be dual to Einstein gravity. So that's the conclusions. But most of the time, I'll try and just emphasize that you can exactly solve the theory just using standard large N techniques for the free energy. Any more questions? All right. So the Euclidean action for theory again is simple. It's just Chern-Simons plus the kinetic term for the fermion. Will work in light cone gauge and in Euclidean space, so that's just involves some eyes. So it's light cone gauge in Euclidean signature, which you can think of as a Wick rotation from light cone gauge in usual Lorentzian signature. So there's three directions: x1, x2, x3. We choose x1 and x2 to be the light cone directions, and okay, light cone gauge is preserved by boosts in Minkowski space. So this gauge is sort of invariant under rotations in the 1-2 plane, which we'll use later. So the advantage of light cone gauge is that there's no ghost, so it's easy to use this gauge, plus the A cube term disappears, and the theory has a very, very simple structure. So it's just the propagator for the gauge field is this, and there's just the vertex between the gauge field and the fermion. Okay, so the first step, if we want to solve the theory exactly, is to obtain the exact fermion propagator as a function of lambda. So it's more, okay, so it's convenient to parameterize this in terms of the self-energy sigma, which is a matrix and a function of P. So the idea is we want to calculate the self-energy sigma exactly as a function of lambda. And there's a simple way of doing this diagrammatically. So say you wanted to calculate the exact propagator. So let this be the exact propagator. Then you'll draw diagrams like this plus plus. Okay, and I claim that other diagrams you would draw at two loops say will be subleading in N. So for instance, if you tried to draw this sort of a diagram, it's clearly subleading in N because using two-line notation. There's no loop, but there's two propagators, so this is quite subleading, whereas here this guy looks like this, so that's, and this is whatever, I mean, lambda squared over n squared. So these are, so only a simple class of diagrams contributes in the large n limit, and of course you can just write this in the following way as which clearly sort of reproduces all the diagrams you would run into. And okay, in terms of sigma, that's just and this should be familiar. I mean, to those of you who study the TUF model, it's exactly the same diagrammatics. Okay, so just diagrammatically we can that translates into a integral equation which I wrote for you here, and the task is to solve this integral equation at 0 temperature and then again at finite temperature. But okay, before I do that, I'll just mention there's another simple non-diagrammatic derivation of this integral equation for the exact propagator. And okay, say you start with the light cone gauge fixed action, and you integrate out the gauge field, which since it's quadratic you can do that, and you just get a non-local action in terms of fermions. Then just using this trick, 0 is the path integral of this total derivative, gives rise to this expression, and working that out gives the relation between the exact propagator and 4-point functions, which in the large n limit factorizes and can be solved to give you the gap equation. So alternatively, you can just, of course, derive everything from the path integral, and the two ingredients are that you use light cone gauge, so you can integrate out the gauge field and large n factorization. Okay, so the question is how do we solve this equation? So I'll just sort of sketch the solution on the board. So any questions so far about this? Okay. So this is his equation for sigma. So first, let's note that sigma is a matrix, so we can write it as times one, and okay, the exact the propagator for the gauge field means that okay, the right hand side of that equation is proportional to gamma 3. So plugging in the gamma weight, actually it's proportional to so involves this sort of this, if you want to process that, you'll run into this sort of an expression, and that this is 0 for, this only picks out the identity component of the matrix A and the minus component. So the point is that when you process that equation, we get sigma equals times from which we can immediately read off that okay, sigma minus equals 0 and sigma 3 equals 0. Okay, so then the only two quantities in the fermion self-energy we need are sigma plus and sigma identity. And okay, because okay, the gauge we have, you know, arguably preserves rotational invariance in the 1-2 plane, and because P3 doesn't appear on the right hand side of that equation, you can scale invariance just forces the only ansatz you can have for the exact propagator is P plus times G naught of lambda and lambda. So scale invariance and rotational invariance just force a very simple momentum dependence on the remaining two components of the propagator, where PS is P1 squared plus P2 squared. And basically there's just two unknown functions of lambda which we want to obtain. So then the thing is just to plug in these functions of lambda into the equation and regulate it and extract an equation which solves for f naught of lambda and g naught of lambda. So we do that and we find the following two equations for g naught and f naught, and these are linearly divergent, but using a dimensional regularization scheme you can get rid of those divergences, and the solutions turn out to be remarkably simple. It's just f naught equals lambda and g naught is minus lambda squared. So then that means the exact propagator leading order n, but all values of lambda is simply given by this expression, and so that means effectively it just only receives contributions up to 2 loops in the large n limit, which is interesting.
Is there any independent explanation of that fact?
I don't know.
Just an observation right now.
There's no good independent. I mean, we did some things in like a light cone Hamiltonian, but yeah. So I don't know why the theory is so simple. Actually, it's just this is what comes out of the thing. Okay, so this is the exact propagator. It's sigma, but we want to calculate, say, a physical quantity, and the simple physical quantity to calculate is the free energy of the theory at finite temperature. That is the free energy on R2 cross S2. So one way of doing this is and the easiest way of doing it is just diagrammatically. So I'll
Right, this is a 3D theory, right? R2 cross S1, you mean?
Yeah. Oh, so R2 cross S1. Sorry. That's it. Yeah. So where the radius of S1 is the inverse temperature. Right. So we want to calculate the free energy, and diagrammatically the log of the partition function is just, in the larger limit, is just given by all the disk diagrams you can draw, which are shown there. And you can just simply rewrite this in closed form in terms of the exact propagator and self-energy as this. So okay, it's interesting to actually work this out order by order, but I'll just do that for you so that it seems less so right. So these are just disk diagrams in the planar disk diagrams that one can draw, and the numbers are just the symmetry factors of the diagrams. All right, so the claim is we can rewrite this as sigma plus where the shaded blob is again the exact propagator. And okay, the first term is just log of the exact propagator, and okay, the second term is, that's just sigma of q times exact propagator. So you can, okay, so I'll leave this as just a sort of exercise that you can convince yourself that okay, I mean this expression gives you all of these guys, yeah, even with the right symmetry factors at each order in lambda. Yeah, so and translated into equations, it's just log of the exact inverse propagator plus a second term, which is needed to get the right symmetry factors. So the free energy of the theory can be expressed exactly in terms of the exact fermion self-energy. So to evaluate the free energy at finite temperature, you just solve the gap equation at finite temperature and then plug in that expression to the previous expression for the vacuum energy, which is related to the free energy just as usual. And to solve it at finite temperature is the usual trick where you just integrals over P3 become sums over Matsuura frequencies, and okay, and that's the standard stuff. So okay, and what's again is surprising is that you're able to exactly solve the gap equation even at finite temperature. So how would that go? That's just okay. At zero temperature, we just have two functions of lambda, but when you have and to obtain these solutions, you have to solve a you sort of run into some coupled integral nonlinear integral equations, but it's just because the numbers are exactly right there's just a simple solution in terms of C tilde, which is this number defined by this equation. And of course, the point is that the numbers in the integral equation are exactly right for it to have a closed form solution. So earlier on, we actually had a mistake, and then we couldn't find the closed form solution. But yeah. Okay, and then plugging that in, you just get the free energy to be given by the following function of lambda. Okay, interestingly, okay, one of the observations is that the free energy goes to 0 at lambda equals 1. So, and so that's like a decrease in the degrees of freedom as you increase the coupling, and the theory probably doesn't exist for lambda greater than 1. So the fact that the theory doesn't exist at lambda equals 1, okay, we propose this is sort of an explanation, is that, okay, we use the dimensional regularization scheme, okay, which doesn't give a shift in the Chern-Simons level k, but if you instead regulate the theory with, say, a small Yang-Mills term, then people have shown in perturbation theory you get a shift in k, and by the rank of the gauge group, which is n. So the theory probably with a small Yang-Mills term exists at all values of lambda, and that would require our theory to only exist for lambda less than or equal to 1. Okay, even if this isn't satisfactory, I mean the same phenomena has been found for like the ABJ theories, which that say for UN cross U1 ABJ, the theory doesn't exist for the large enough values of the 't Hooft coupling.
There's a big difference though, because here you don't have supersymmetry.
Yeah, there's no supersymmetry.
But supposing one just took your model and supersymmetrized it minimally, like n equals 2 supersymmetric vector model, do you know if this kind of formula would still hold?
I think it would still hold, yeah.
Maybe we should talk about this later.
Yeah, okay, so this is, okay, so the point of this is just that, okay, I mean, using light cone gauge and just working through the diagrams, you can exactly solve the theory, at least any given quantity you want to calculate without really using supersymmetry. But okay, then next we'll turn to a different thing, which is the question is what can we say about the holographic dual? So any more questions about the previous section questions?
Can I just ask?
Yeah.
I mean, so you say lambda equals 1, it doesn't exist, or greater than 1.
I mean, it goes to.
I mean, it's weird that it goes to 0 degrees of freedom.
Okay, but okay, if you were thinking of the partition function, say on S2 cross S1, instead of R2 cross S1, then this is sort of the coefficient of the T cubed term.
Yeah.
So that vanishes as lambda goes to 1. Maybe there's subleading guys that don't vanish.
Yeah.
So it's you can think of it that way if you want to. That's just because R2 maybe isn't good. You might would rather do it on S2. Right. Okay. Next we just looked at a slightly different question. What can we say about the holographic dual to the series? So again, this is just a short and simple thing. So say we consider the limit of lambda going to 0 where the theory is free. So that's just free fermions in 3 dimensions. Free theories have infinite number of conserved currents. Okay, one for each spin. So spin 1 and spin 2 are just the usual conserved current and stress tensor, but you also have higher spin symmetries, which for instance come from this symmetry, and hence the dual theory would have a higher number of holographic tool will be a higher spin gauge theory with one gauge field for each conserved current, and it's of course it's well known what that dual theory is. It's been conjectured. It's pretty established. It's a particular Vasilyev theory that people have constructed, whereas which maybe makes this more interesting because we actually have a description of the dual theory. So we would like to see if we could explicitly see these higher spin gauge fields becoming massive or something. But and for instance, the conserved currents, you can work out what the conserved currents are for any spin. And for example, the first 4 conserved currents are these. So this is just the conserved U1 current, the conserved stress tensor, and then the spin 3 current. Okay, these are the numbers that come out. And the spin 4 current you have is more complicated. And okay, so these are all single trace operators in the sense that you have one fundamental and one anti-fundamental and one fundamental index contracting each other, and with some derivatives inside. So those are like the analog of. So that's what we'll call single trace by analogy to the large N limits of matrix models. And okay, there's much fewer single trace operators because you can only have 2 fermions, whereas if you're doing matrix models, a single trace operator can have a long string of fermions. Here you just have one, psi bar something inside psi, and that's all the single trace operators you have. So the question is, we want to ask what happens to the higher spin gauge fields as we turn on interactions. So if you want the bulk higher spin gauge fields to become massive as we turn on lambda, you want, on the field theory side, the higher spin currents should attain large anomalous dimensions at leading order in 1 over n. And of course, we can show that the anomalous dimensions are actually sort of protected by conformal invariance in the large N limit. So actually the anomalous dimensions of all these currents vanish at leading order in the 1 over n expansion for all values of lambda. Okay, and the argument is really sort of simple, so I'll just sketch it. Is okay, unitary representations of the conformal group are labeled by just by the scaling dimension of their primary state and the spin of their primary state. So okay, so this is how you characterize representations delta comma s, and unitarity forces the constraint that delta in 3 dimensions, that delta is greater than or equal to s plus 1. And representations which saturate this inequality, like delta equals s plus 1, are short. Okay, and hence they're sort of protected, and if you want them to become long representations, you have to combine them with another representation of the form s plus 2 comma s. Okay, this is just conformal representation theory. So let's look at the single trace operators that we constructed. So aside from the single trace operators correspond to the following representation. So there's 2, 0, which is just psi bar psi, and then the remaining ones are j plus 1 j. So for instance, psi bar psi. So this is spin 1 and delta equals 2. And then then at each higher spin you just add one derivative, so s increases by 1 and delta increases by 1. And so this is the conformal representation content of the single trace operators. So other than the spin 0 guy, they're all of the form j plus 1 comma j, so they're all short representations, and that's That's obvious because they're conserved, so that a short representation is a conserved current. So now we want these guys to obtain enormous dimensions, and that means they have to turn into long representations, because short representations you can't just change delta without changing s. And to do that, you need another long representation of the form j plus 2 comma j. Now, okay, we know that the spin 1 and spin 2 currents don't acquire enormous dimensions because they're exactly conserved for all values of lambda. So let's start at J3. So J3 has spin spin 3 and mass dimension 4, which is and it's short. So if it was to combine, if it was to have an enormous dimension, it would have to combine with an operator with spin 2 and mass dimension 5. This is what follows from conformal representation theory. But if we're going to restrict ourselves to single trace operators, then the only spin 2 single trace operator has mass dimension 3, and that doesn't get renormalized because it's conserved. So there's nothing for the spin 3 guy to combine with to turn into a long representation, and hence it can't acquire an enormous dimension. Okay, then you look at the spin 4 guy, and because the spin 3 guy stays short, there's nothing for the spin 4 guy to combine with, and so on and so forth.
Spin 4 guy is 5, 4, right?
Yeah.
So it would like to combine with what? I mean, it could
With
combine
a
with more
3.
than one thing.
No, it would have to
What determines the things it can come mixed with?
It has to just mix with one less spin.
One less spin, so 2.
No, so spin 4 guy would have the
four
spin 3 guy has
would have to mix with spin 3.
Yeah, and with and the mass dimension has to be such that it's a long representation. So a short representation of spin s becomes long if it mixes with a long representation of spin s minus 1.
Okay. So if you never get a long representation, you never get a long. It's that sort of cyclic. Once you show that, it's like by induction.
Yeah, it's just by sort of induction. Okay, because and the starting point is this, say, the stress tensor, which has to be conserved. Okay, but the point is this works because we're only considering single trace operators. If you had a matrix model, you have there's many more single trace operators, and this argument doesn't hold. If you're away from the large n limit, there's no reason to restrict yourself to single trace operators. So then you have more guys to mix with, and this doesn't hold. Okay, so that's basically it. Then you might ask, okay, but obviously the currents aren't conserved in the interacting theory, the higher spin currents. But the point is they're sort of almost conserved in the sense that their divergences are multi-trace. And okay, that means that, say, for example, so for instance, J3, it's divergent when you take into account interactions. It's a product of multi-trace operators, and if you normalize the things carefully, then that means within 2-point functions, it's effectively conserved. At least the leading order in n. There will be subleading 1 over n corrections, but the leading order thing in n is conserved. So that's sort of how it works. And yeah, this is just saying the same thing. And you can even calculate the 1 over n corrections to the enormous dimension leading order in lambda by calculating the divergences of these currents. But that's not important. So then the conclusion is just that, okay, these higher spin currents are still there in the field theory side, and hence in the gauge in the bulk. Okay, if you have a holographic description, the higher spin gauge fields have to be at least locally massless. And okay, I think so that's it. So if this suggests that the holographic dual has to be a higher spin gauge theory. So that's the main conclusions of the talk. So
sorry, the holographic dual has to be a higher spin gauge theory whose currents are not exactly conserved.
Whose currents are not exactly conserved. So that
isn't this sort of the inverse of this Maldacena theorem?
the theorem that came maybe in
for your paper here.
Yeah. So this is not inverse. I mean, it's related.
I thought he said if higher spin currents are exactly conserved, then the dual theory is free.
I know, if high spin currents are exactly conserved, the theory itself is free.
Oh, the theory itself.
You might have these high spin currents. Does that necessarily mean it's a free theory?
Mm-hmm.
And
okay, that's a difference.
He also talks about this thing a little bit. But I mean, yeah, a simple thing. This is just. But okay, these are currents which are almost conserved, not quite, and the idea is in the dual description that have to come from some sort of boundary conditions. So in the critical ON vector model, I mean, Simon and G had found the similar thing. The currents are all not quite conserved in the critical ON vector model, but they know how to get that non-conservation from boundary conditions or something. And the idea is something similar should work here, but I don't think we've got the actual recipe for the dual yet. But that's it. So, but anyway, so the point is just the theory, the UN Chern-Simons theory coupled to a single massless fermion is solvable, so we can compute the partition function, say on R2 at all values of the 't Hooft coupling, and okay, I mean the tower of higher spin currents suggests that the bulk dual is a higher spin gauge theory. Okay, so outlook is okay. I mean the point is okay. Again, as I said in the beginning, there's a lot of lines of conformal fixed points in 3 dimensions. Okay, for example, okay, we might want to study. Okay, and okay, one sort of immediate conclusion is this counting thing sort of applies to any vector model practically, with minimal changes. So say you consider UN cross U1 ABJ theory. That's sort of a vector model. So its dual is like a higher spin gauge theory probably, and I think G has a good candidate for what that supersymmetric higher spin gauge theory is. So in this sense, whatever the stringy construction of ABJ is, it also gives you a higher spin gauge theory. That's.
So there's an equivalence between string theory and higher spin gauge theory in the same dimension?
I think it should be. I mean, because the point is the dual to a vector model would be a higher spin gauge theory. I mean, of a Vasiliev type, so it's not complicated like the dual of, say, super Yang-Mills at lambda. And the point is, well, okay, UN cross U1 ABJ theory is, morally it's a vector model. So its dual is a Vasiliev theory. So whatever the construction is of the dual of ABJ, which is like, I guess you have some flux on the CP1 or something. So that should give you a higher spin gauge theory. So and that's quite interesting because you might want to see exactly how does that come about. So that's something G is sort of looking at. Okay, another different. Okay, and just maybe to emphasize that a bit more, we can. Okay, I mean so it also would be interesting to go from UN cross U1 to UN cross UN, because at m equals 1 you just have these sparse single trace operators, but as m increases they sort of get beaded together to give you the usual strings of multi-trace operators. So in that sense you can it suggests that as you go from m equals 1 to m equals n, these higher spin gauge fields sort of combine to form strings. So that's something I want to investigate. And Yeah, on the other side, okay, just as I was saying earlier, that you have all these non-supersymmetric lines of conformal fixed points. So it's just UN cross UN Chern-Simons theory with pi-fundamental fermions. Is that dual to some simple non-supersymmetric theory of gravity in ADS4? So that would be interesting. But yeah, that's it. So that's all I have to say. Yeah.
Any questions?
Still have one, if I can.
Yeah.
If you could go back to that relation between lambda and lambda Yang-Mills,
Yeah.
I think there's a claim that, or I think it's known that lambda Yang-Mills, what you define as lambda, so here you said lambda k Yang-Mills gets shifted by sine k Yang-Mills times n
Yeah.
in the non-supersymmetric theory.
Yeah.
However, if I understand right, with n equals 2 supersymmetry, it gets shifted by maybe half of that amount or something, and by the time you have n equals 3 or more, I could have the details wrong, then it doesn't get shifted anymore.
Okay.
So, in that case, the relation between lambda Yang-Mills and your lambda is not what it says here if you have some supersymmetry.
Right. Okay. I mean, we have to check, does the dim reg guy get shifted, or assuming that never gets shifted? I mean.
Yeah.
Oh, you're saying in comparison to what you
Well, it's
get from
unlikely
dim
the
reg.
dim reg gets shifted when you have supersymmetry and not when you don't have it.
Right. Right. So yeah, then it would change. So this is.
So that suggests a prediction that your lambda equals 1 breakdown will not happen if you have maybe even just a little supersymmetry.
Yeah, we can check that. But okay, I mean, even ABJ theories don't exist, right? I mean, I think that had been.
Yeah, that's the puzzle. Anyway, we should talk about that.
And that also is okay because the dual is a higher spin gauge. So you can't take lambda to infinity. So that's a physical interpretation of that. But yeah. Okay, but that's it. So. Okay. Yeah.
Any other questions? Okay, let's thank the speaker again.
Yeah.